Let's jump right into this explainer. Today, we're opening up a shared study journal to sketch out the fundamental rules of matter. Here's a super quick look at the chapters we're sketching out today. Welcome to Chemistry, Building Blocks and Bonds, Mixtures and Physical Changes, The Secrets of Solubility, and finally, the Mini Scientist Assessment. Let's get to it. Chapter 1. Welcome to Chemistry. Let's start right at the foundation. At its core, chemistry is simply the study of matter, and it basically relies on three main pillars. First up, composition. Like, what are the actual building blocks? Second, properties. Is it a solid crystal like salt or a liquid like water? Properties help us categorize everything. And third, changes. How does it react with other things? Together, these three pillars help us totally decode the physical world. All right, Chapter 2, Building Blocks and Bonds. Let's zoom all the way in to see exactly what makes up our universe. At the absolute simplest level, we've got elements. An element is a pure substance made of only one type of atom. Think of it as the end of the line. You just can't break it down any further by chemical means. These are essentially the ultimate cosmic building blocks. Things like hydrogen, oxygen, iron. Pure, simple, and fundamental. But things get really interesting when those distinct elements decide to kind of hold hands. When two or more different elements are chemically bonded in a fixed ratio, they create a compound. And here is the real magic trick. A brand new substance is born with entirely new properties. Take two hydrogen atoms, bond them with one oxygen atom, and boom, you get water. That chemical bond literally changes everything. Chapter 3, Mixtures and Physical Changes. But what happens when things mix together without actually holding hands? Well, unlike compounds, in a mixture, particles are physically combined, but they are not chemically bonded, meaning they keep their original identities. A homogeneous mixture is evenly blended, like the invisible gases making up the air we breathe. A heterogeneous mixture, on the other hand, is chunky and uneven. Think of a handful of trail mix. Because there are no chemical bonds holding them together, you can usually separate mixtures pretty easily. This actually helps us understand the two main ways matter transforms. Dissolving solid salt into liquid water? That's a physical change. No new substance is formed, and it's super easy to reverse. You just evaporate the water. But chemical changes? Oh, they're one-way street. Burn a piece of paper, and it turns into smoke and ash. Let bacteria act on milk, and it transforms into yogurt. Those are irreversible chemical changes where completely new substances are born. To keep this all straight, we have the matter diagnostic matrix. It's basically our cheat sheet to visually check for bonds. Elements, no bonds. They are simple and pure. Compounds are chemically bonded in fixed ratios, creating totally new things. And mixtures are just physically combined. They're mixed together, sure, but not permanently joined. So it's your turn to play scientist for a second. Where do you think H2O, air, trail mix, iron, and CO2 belong on this board? Think about whether they're pure, bonded, or just mixed up. Got your guesses? Okay, so iron is pure, that's an element. H2O and CO2 have strong bonds, those are compounds. And air and trail mix, they're just hanging out together, so those are definitely mixtures. Moving right along to Chapter 4, The Secrets of Solubility. Now that we know dissolving is a physical change, let's explore exactly how things dissolve. Before we dive deep, let's establish that solubility is essentially a story of capacity. It's the maximum amount of a solute, like salt, that can dissolve in a given amount of solvent, like water, at a specific temperature. Basically, how much can a liquid hold before it simply refuses to take any more? Think of it kind of like a party for particles. An unsaturated solution has plenty of room. It is literally hungry for more solute. You could add more and it would just vanish into the mix. But a saturated solution, that is a completely stuffed full house. The absolute maximum amount has dissolved. If you try to add even one more pinch of salt, it won't dissolve. It'll just stubbornly sit right there at the bottom of the beaker. But here's the thing, that capacity isn't fixed. Temperature is the magic key here. As the temperature of the water rises, the line on our graph curves upward. Heating a liquid expands its capacity for solids, making them way more soluble. Interestingly enough, for gases, it's the exact opposite. And if you add pressure, like, say, keeping the lid tightly screwed on a soda bottle, you actually force more gas to stay dissolved. Change the temperature or the pressure, and you completely change the rules. And that brings us to Chapter 5, the Mini Scientist Assessment. We've covered a lot of ground today, and now it's time to put your new chemistry lens to the test. Take a quick moment to focus. This is the part where you get to think like a true scientist. we're going to apply everything we've just uncovered about changes, mixtures, and solubility. You've got all the tools you need right here. Take a deep breath, trust your effort, and remember that every single step in this explainer brings you closer to discovery. All right, let's look at the data. Okay, imagine a beaker of perfectly clear salt water. The salt is completely dissolved. First question, is this salt water an element, a compound, or mixture? Well, since dissolving salt is a physical change and no new substance is formed, it's absolutely a mixture. Second question, look at the coordinates on our graph. Your solution falls right below the green solubility line. Because it's under that maximum capacity line, it's unsaturated. It's still hungry. If you added one more spoonful of salt, it would easily dissolve. See? You completely nailed it. Chemistry can definitely be tough, but breaking it down visually makes all the difference in the world. So, as you go about the rest of your day, I want you to look around your kitchen or your classroom, or even just look at the sky outside. Ask yourself, what invisible chemical reactions and what physical mixtures of solids, liquids, and gases are happening right now in the room around you? Keep exploring, and I'll catch you on the next one.